Hello everyone, today I'm going to talk about neural supersampling for real-time rendering. First, some introduction about this. As we all know, display resolutions and demands for photorealistic visual quality is increasing. For example, for the virtual reality headsets, they require 2880 by 1600 pixels at 90 to 144 Hz. For the recent gaming monitors, they require 3840 by 2160 pixels at 144 Hz. So the requirements are pretty high, so the paper will not target on the requirement, but they will get close to it. So in order to achieve the requirement, instead of rendering in high resolution directly, the game engine will render in low resolution first and do upsampling to the high resolution. Supersampling concept comes from the super resolution problem in computer vision field, but there's a main difference between them. In computer vision, for a photorealistic image, they consist of pixel area integrals. But in the real-time rendering, the result only contains of point samples, so that means the results are very noisy. So in this context, we need to deal with both anti-aliasing and interpolation problem. Here are problem settings. There are two main problems in the paper. Input images with point sample pixels are aliased as shading and edges, and information as a target to be interpolated pixels is missing. What does that mean? When we map from low resolution to high resolution, there must be some pixels we don't know the value, right? The paper wants to use color, depth, motion vectors in different frames to address the problem. When we have the different frames, we can project to the current high resolution frames, so we are more likely to have more pixel values. But when we use some motion vectors, there are pros and cons too. The motion vector can provide candid matching between pixels for low cost, but the pixels at the previous frame cannot be directly projected to current frame because of occlusions and changes in lightning and reflectance. For example, here are the two images, frame I-1 and frame I. We know the correspondence, but we can't project the pixels in frame I-1 to frame I directly because of the occlusions. Network overview. The input of the whole network can be separated into current frame and the previous frame. So we will start from the previous frame. So for each previous frame, they will go to feature extraction neural network and go to temporal projection part. So the goal of this part are project the previous frame to the current frame. But we know in this part, the dynamic occlusions and shading changes are not considered. So the feature reweighting network will help to consider about it. And then after that, the current frame and the previous frame information will send to the reconstruction network to reconstruct the high resolution current frame. There's one thing to notice is that for the current frame, they change the color space from RGB to YCBCR. The reason they do that is because they do some experiment about that, and they found that when using YCBCR, the quality improve a little bit. So they do this. For feature extraction, the input is color and depth map. They go through 3 convolutional layers to get 8 feature channels. So the color and depth will concatenate with the 8 feature channels, so the total are the 12 channels. Temporal projection. The goal of this part is to project pixel samples and learn features of previous frame to current frame. So when we finish feature extraction, we have 12 channels. For each channels, they do zero upsampling and backward wrapping. For example, we have one channel feature map in frame I-1 and then do zero upsampling to like this. So what is zero upsampling? That means for 1 pixels in frame I-1, we put the pixel values in the corresponding positions in high resolution map. And when finish this, the other part are all zero. So for the motion vectors, because motion vectors are continuous, so when they map from low resolution to high resolution, they use bilinear upsampling. So that means for each pixels in the high resolution, they have corresponding motion vectors. Then combine these two, they can project to the frame I. Because motion vector is defined for an adjacent pair of frames, so when we want to project the frame I-1 to the counter frame, we need to do backward wrapping iteratively. So first we need to project to the I-1 and then frame I-2, I-1 until to counter frame. Feature weighting. So for motion vectors, we know that they don't reflect dynamic occlusions and shading change. So the feature weighting module is to mask out mismatched samples. The input of the module are RGBD of Hall frames. They will go through 3 convolutional layers to get 4 channels output. For one channel, it's basically a pixel-wise weighting map for one previous frame. We have like 4 previous frames, so we have 4 channels output. After that, they will multiply features of each previous frame to get the output. Reconstruction. The input of this part is features of current frame and row-weighted features of previous frame. And then they will go into a UNet to reconstruct the current high-resolution frame. I won't go into details about UNet. You can reference this paper. Now comes to the loss functions. The loss functions are constructed by 2 parts. One is structural similarity index and another one is perceptual loss. So I will introduce it one by one briefly. X here means the network output, X bar means the ground truth. So for the structural similarity index, they compare luminance, contrast, and the structure. The structure here mainly means the mean square error of normalized images. For more information, you can refer to the reference one. And the second term is perceptual loss. The aim is to measure perceptual and the semantic difference between images. So the author thinks pre-trained image classification network have already learned to encode the perceptual and the semantic information. So they compute a loss based on the pre-trained VGG network. So the I here means layers in the VGG network. They basically compares the output of the layers. Here is the result of time efficiency. They target on 3 different high resolutions. And hours and hour fast are 2 hyperparameter settings. For hour fast, unit output channels of each layer reduced by 50% compared to hours. Then we can see in the time breakdown of the module, we can see that the reconstruction part are dominant. By the way, they didn't compare the time efficiency with the other paper. Here is one result of the paper about the image quality. So the paper they compare in reference one. They compare with a lot of paper, but I will just show one here for one thing. About limitation, so just like the other neural network approaches, the generalization ability of this approach is not that good, and they will also fail in one case when the multiple inputs contain too little information. That means the inputs are too noisy. So just like the examples I present here. That is pretty much all for my presentation. Thank you for your listening.